continuing with the course, and I'm going to be talking about the applications of the interior maximum principle. So, this is sort of a geometric way of looking at what the maximum principle says. It says if you have two connected minimal surfaces in R3, and you have an interior point of both surfaces, so it's this sort of picture. Here's the first surface, here's the second surface, M2, and they have the same tangent space, okay? And one surface is locally on one side of the other surface at a point. Then in the neighborhood of the point, the surfaces agree. And the surfaces are analytic, so they just keep agreeing for a long time. So this is also a standard kind of argument that people use when they study what are called false branch points. They kind of do a similar kind of idea. And so you can just continue being the same until you get to the boundary of the surfaces, assuming the surface is smooth with boundary. Okay, so, all right, so, yeah, and you're kind of using the fact that they're locally graphs, and then graphs of minimal surfaces satisfy certain PDEs, which have maximum principles. So, okay, so that's one thing. And so this is just this, I always found this to be very, very simple, very nice application of the interior maximum principle. And it says that if you have let me erase this. It says you have the following picture. So you have R2 down here. You have, I'll state it a little differently. You have a curve in the plane, R2, which bounds a disk, D, in the plane. Over this, we have the cylinder, vertical cylinder, in R3, over this sort of solid cylinder over the disk. And if you translate what I said there, what I'm saying is that suppose you have a Jordan curve, a curve gamma, in R3, we have our projection pi down onto the plane, and suppose that the projection of this curve down to alpha is a one-to-one projection. So this curve is a graph over this convex curve. So this is a convex curve, convex Jordan curve in the plane. Then the claim is that this curve bounds a unique minimal surface, compact minimal surface, and that compact minimal surface is a graph. So this is one of my very simple, nice application of the interior maximum principle. Okay, so let's just start that. Where's my little clicker? Okay, so, all right, so we start with a surface, and I'm going to start with a surface that's not a graph. Okay, so maybe it looks like, maybe it has a handle or something on it. Maybe it's just not a graph. Maybe it's a disk topologically, but just not a graph. But anyway, I'll just draw a picture there. So we have our surface, and we have the disk that bounds the curve. We have, it's not a graph. Okay, so this surface is certainly not a graph. If it was a graph, it would be a disk. So we have a point here, actually in the interior, over which we have, maybe I should redraw a point here. And if I draw the vertical line over here, it's going to intersect the surface in more than one point. That's what it means to not be a graph. Okay, so in this picture, that vertical line is intersecting 1, 2, 3 points. But if it's not a graph, I have at least 2 points. In the background, we're using the fact also that minimal surfaces satisfies the convex hull property, and the entire surface, it's again using the fact that coordinate functions are harmonic functions, the entire surface lies inside the solid cylinder. So the interior of the surface goes into the interior of the solid thing. So this point here where you're not a graph is happening at an interior point of the disk. Okay? So we have at least 2 points. So we have a point P1, a point P2, which are in the pre-image of that point. In other words, on the vertical line above the point. And then you can write down the vector v, which is P2 minus P1. Okay? We can think of taking that, I do with my mouth, my little clicker right here. Okay, and we can translate the surface up. So we can take the surface, and which I'll call M. M's our surface, and I'm going to translate it up by this. So I'm going to take P2 minus P1 plus, let's call M hat, plus M. Okay, so I'm going to translate the surface vertically up, and when I do that, the point P1 is going to translate up to the point P2. So this is the vector that we're talking about, the vector v. And so this surface here, which is the translated surface, is going to intersect the original surface at the point P2 in this case. So at P2, you notice the P1 is going to translate up to P2. P2 is on the other surface. So they're going to intersect the point P2. Okay, so that's what we have. We have somehow this translated surface up. Now, if we translate up by a big amount, we keep translating. Eventually, since the surfaces are compact, they don't intersect at all. And you can kind of think of translating down. There'll be a first time that they will intersect. And that's by compactness. Okay, a sequence of points which intersect, and you kind of go, subsequence will converge again by the sequence of translation, so at a point of intersection. You have a bounded sequence of points and they'll have a convergent subsequence. Anyway, a little thought shows that there is a largest vertical translation such that these two surfaces intersect. And since they intersect at a point, right? So there's some point in the intersection of those two surfaces. So this is kind of this picture. I'll draw it like this. So here's M plus some kind of 0, 0, t. And here, which is somehow the highest surface, and I claim I have this sort of picture. Here is the original surface M. So I've translated up by a biggest amount, and I get some kind of point on the surface of intersection. So here's my point Q. And I claim that this surface must be on one side of that surface. If it weren't, then I could translate up a little bit more, and I would still intersect at some point. Okay? So this surface must be on one side of that surface. And so I can apply the one-sided curvature, this maximum principle at this point. So that would mean that these two surfaces must agree until you get to the boundaries. By analytic continuation, these are analytic surfaces. They have to keep on agreeing. Well, that's just impossible. So by the maximum principle, these must be the same surfaces. Because the boundaries don't intersect at all, right? So they're going to you keep on trying to be the same, but they can't keep being the same because they have different boundary curves. The boundary curves are disjoint. Okay, so that's a real nice application. And it gives you a good idea because it gives you an idea about deforming. So you can do deformations by translations. And then we're going to do now a new proof of also going to get a nice global result, which is a deformation, but not necessarily by translating the surface. Okay, now on this, I basically proved it had to be a graph. Why does it have to be a unique graph? Another part, if you look at number 2 in the statement of the theorem, it says it's a unique graph. Not only is it a graph, but it's unique. Why is that? And it's the same argument. If it weren't unique, then you would have 2 graphs. A graph, say, here, and maybe some other graph like that. We'd have 2 graphs, graph 1 and graph 2. But again, if you have 2 graphs, then you can translate one up, right? If they're not the same graph, you can translate them up by something, and they will intersect in the interior. and then you do the same argument. You translate it up as high as you can. You translate, say, this one up as high as you can, and they intersect. But then, by this principle, maximum principle, they must agree. But they have different boundary curves. The boundary curves are disjoint. One's above the other one. So the same argument shows uniqueness. Now, it turns out, maybe I'll just work a little bit more on this. It turns out there are lots of places where we'd like to generalize this argument. And we have difficulty generalizing this argument for who knows what reason. But so that sometimes it's useful to be aware of another argument that's very different. And that argument works. Okay, this is especially a notice to Alvaro, who's worked on a similar question in certain homogeneous spaces. So you look at certain minimal surfaces, and you want to prove that they're graphs. Okay, so what's this other one? That's originally people didn't, I guess, realize one had this kind of very simple proof and a very general argument here. Radeau came up with another argument that showed in this setting a minimal disk are graphs. So I'm just going to give that argument since it's very useful in other contexts where we don't have translations. So how do we prove, well, we have other things. We have like planes or something, minimal planes. So let me give that other argument that's due to Radeau. And what he shows is he doesn't use the maximum principle here, but rather here's the plane, here's our curve. He assumes he has a disk. Okay, so here's your minimal disk, but it's not a graph. Maybe it's not a graph. He wants to prove the minimal disk must be a graph. Okay, so it's a very different argument. So again, you look at the projection, and you take the projection from the minimal surface down to the disk. And what it means to be a graph, it just means that this is a one-to-one projection. Okay? Well, when will it be a one-to-one projection? Well, suppose it's a submersion. Then by covering, and it's an identity, it's one-to-one on the boundary. If it's a submersion, then this will be a covering space of the disk. But the disk is simply connected, so this will be one-to-one. And what does it mean to be a submersion? It just means the tangent space at the surface at each point is never vertical. At a point, you're not a submersion means you have there's some vector in the kernel of the projection. That means in the projection, the kernel of the projection of this operator is vertical vectors. So if it's not, then there exists a tangent plane to the disk, I'm assuming we have a minimal disk, that there exists a tangent plane that's vertical. Okay? And so we're going to use a little different argument. So here's my plane. Okay, so the failure to be a graph is just the failure to be a submersion, which is just the existence of a vertical tangent space. Okay? Okay, I'm going to assume that's in the interior. Okay, so here's my vertical tangent space. So the question is, how does that vertical tangent space, well, it intersects the surface at a point. How do they intersect? And a tangent plane is a minimal surface. The surface itself is a minimal surface. And you can view that other minimal surface is a graph over it. And the difference of somehow those functions kind of looks like a harmonic function. And the zeros of a harmonic function on the plane are given by harmonic polynomials. And they give you like crosses, somehow curves that give you a cross with equal angles. So harmonic polynomials on the plane have a very special kind of zero set. Equal angles, they're given by homogeneous harmonic polynomials. I mean, this sort of infinitesimal sort of picture. So that means that back on M is a disk topologically. So here's M. It's mapping into the space by our immersion here. And what I see on it, it's locally, assuming it's immersion, The intersection set. So if I look at TP of M, this vertical tangent plane, and I take, let's call this mapping F. So I look at the inverse image of this surface. So at the point where we have this intersection, call it Q, I see locally like a little cross, and then I keep on going. So somehow I get something like that, okay? So I get a non-trivial cross. I get at least a cross. Okay, so I get across this sort of X picture here. I get an analytic set. So I get this analytic curve, so not curve, but one-dimensional analytic set, which is how the plane intersects the surface. Back in the pre-image, okay? Now, notice that how does the plane intersect the boundary curve? It intersects the boundary curve. The curve has a convex projection on this convex curve. So it intersects the boundary curve only in 2 points, kind of like the picture I drew. Okay? But remember, we have at least two crosses here. And when you look at this analytic set, it separates the disk into several regions. Well, at least 2 regions. So maybe, say, this region. And we're going to always see that there's some region that's like a little disk. So here's a little sub-disk, which might have more things in the plane. But I'm just looking really at this component here that corresponds to that. So there's always going to be a subdomain which has its boundary in this vertical plane. But that's impossible. The coordinate function orthogonal to the plane is a harmonic function. It has 0. Think of that as plane that's going through 0, going through the origin here. It's like having 0 boundary values. Anyway, it's not contained in the plane. It fails the convex hull property. So that means you can't have vertical tangent planes. The absence of vertical tangent planes, the convex hull property then implies this is a submersion. If it's a submersion by covering space theory, it's a graph. So this is an alternative way to sometimes prove things are graphs in the absence of being able to translate the surface. And so it comes up a lot in homogeneous spaces, this kind of argument. We'd like to prove uniqueness of the graph, but we know everything's a graph, or we reduce to knowing everything's a graph. But we still don't know how to prove graphs are unique. Presumably they are, but in certain settings, but we don't know how to prove uniqueness. So we're just kind of waiting for a proof in this kind of setting. Okay, so anyway, this is a very interesting, nice result. It motivates lots of questions about global graphs, other kinds of questions. All right, but we're going to focus right now on sort of generalizing this idea of deforming minimal surfaces and having a last point of contact. So we have this nice application of the maximum principle, elementary application, which says that if you have a proper, say, embedded, connected, non-planar minimal surface in R3 with boundary, you can't be contained in a half space. So proper is important because we want to have, if you remember, there are complete minimal surfaces in the unit ball. I don't know about embedded, but they're complete non-proper minimal surfaces in the ball, which is in a half space, and the surfaces are not flat. So this is really, we really need the word proper here. Otherwise, it's just not true. So proper immersion means in a compact part of the space, I see a compact part of the surface. Okay, so what's the argument? So I'm going to have a picture here in a second. So let me just get to that. But I'll draw this picture also over here. And there are lots of different variants on this proof. So I'm just going to give one variant on the proof. There are lots of different ways of modifying the proof. They're equally kind of easy, but I'm just going to take a particular one. Okay, so we consider our surface, and let's suppose it lies in the lower half plane, lower half space. So think of this as the xy plane, and suppose we are lying below. So this is x3, equals 0. So the height, we have the third coordinate function, or the z coordinate, and it's 0. We have this sort of one-dimensional picture. I'll try to draw the two-dimensional picture. It's a little hard to draw, but okay. So we might as well assume that after vertically translating the surface, somehow it tries to be asymptotic to this plane at infinity. So we can assume that there are points on the surface whose third coordinate, remember the surface is down here, m, and the third coordinate is 0. We can kind of translate it up as high as we can. Okay? It lies in the smallest closed half space below here, and we can just kind of translate it up. So somehow it gets close to the surface. So as you go to infinity, there are points P1, P2, whatever, Pn, that somehow are trying to get to the plane. Notice by the maximum principle, it's disjoint from the plane, because the plane's on one side of it, and we're saying the surface is not a plane. So they get close to the plane, but they don't touch the plane. So here's the origin. So I'm going to pick the unit disk around the origin. That's a compact set. And since this surface is proper, and they live in R3, the distance between this compact set and this set is positive. There's some definite distance. The distance from here to wherever that surface is positive. Okay? All right. So there's a little room. There's a little room here. So I'm going to look at the solid cylinder over the unit disk. And in fact, if I make that solid cylinder of this is going down. So when I draw this picture, this is on R2, and this is at kind of say height, I guess in the picture, minus epsilon. This is at height minus epsilon. So we have our top disk at height 0. We have this bottom disk at height epsilon. And the whole solid cylinder is, again, a positive distance from the surface. And so so we can, for example, make epsilon small, and I guess let me just make sure I make the right picture. I could put a catenoid, an end of a catenoid, kind of like this. So here's the top half of a catenoid. And I could put it with its boundary curve at height minus epsilon, and the whole intersection below the half space, below this plane, all lies in this solid cylinder. Okay? And I can also think of, I could try to translate the thing up. I want to kind of think of this bottom circle being at height 0. But anyway, I can think of doing homotheties or dilations from this point. If that was the origin after translating up, then this would just be homotheties. So I'm thinking of homothetic shrinkings. So then you have to understand what does the catenoid look like. So we take C of t. Okay, where's my mouse? That little thing again. What did I do with it? It's over there. Okay, thanks. Should hold it. Okay. Okay, so we have this sort of picture. We start doing homothetic shrinkings, and you need to understand approximately what a catenoid looks like. It kind of looks like the graph of log r, and it's a surface of revolution. Well, log r becomes very horizontal, so when you homothetically shrink the graph of log r, it converges to the x-axis. So if you're looking at log r, and you do homothetic shrinkings of it, it converges. It's very flat. You're pulling those points back, it converges to the positive real axis, this curve. For the same reason that when you homothetically shrink from that point at height minus epsilon, you do these dilations, those catenoids converge to the plane at height minus epsilon. But remember, there are points Pn which lie above that plane. They're going up to height 0. So, okay, but that's a continuous deformation. So as we do the deformation, there has to be a first time of contact. There has to be a largest t such that, okay, where there's a largest t prime, well, it depends what, how you do the homothety. But the smallest or largest T prime so that the catenoid will intersect. So we get this sort of an intersection, but that's impossible. Get this first point of contact during this deformation. One surface lies on one side or the other, so they must agree until they hit the boundary. But during the homothety, these, notice all the boundary curves of the catenoids, they lie inside a region which are disjoint from the surface. This whole solid cylinder was disjoint from the surface. In particular, the boundary curves under these dilations are all disjoint. So, so we end up with a contradiction. So there's the first time the catenoid touches, the catenoid with boundary, but the boundaries disjoint from the surface when we do this. But then we contradict that they must match up until they touch the boundaries. So anyway, so that's the proof for that. So this turns out to be a very useful tool for doing certain things. So one of the interesting things, consequences, is what's called the strong half-space theorem. So it says if you have two properly immersed minimal surfaces in R3, whatever, one down here, and they're disjoint. So we have an M1 and we have an M2, and they're properly immersed. If they don't intersect, then they must have been parallel planes. That's the only way you can do this. So again, this has lots of applications. One of the applications I talked about before was if you take a minimal surface in a flat torus, a flat 3 torus, and you lift it to R3, and that surface is not flat, then the preimage in R3 is connected. The preimage is a bunch of minimal surfaces. And if they're not flat, then I'll have components. If they aren't connected, I'll have components which are disjoint. Okay, so we kind of use this already. It tells you properties about actions of translation. You know, if you go to a quotient space, what happens under translations, some connectedness properties. Okay, so how do we prove this? Okay, and I'll just think for the moment they're both properly embedded. It doesn't change. So let's assume that the surfaces are embedded. And one of the nice properties of a properly embedded surface is it separates space into two regions. Okay? A properly immersed may be several regions. Okay, so it depends on maybe an infinite number of regions. But when you remove a properly embedded surface from space, you have two regions, one side and you have another side. It always separates and there's two sides. Well, the other surface is on one of those sides. So it's going to separate that side into two pieces. And one of the pieces will have the other surface on its side. So there's a region between them, a unique region between them, where they're both part of the boundary of that region. So there's a region between them, R, call it R, whatever. A region between them that has both surfaces for their boundary. And then I mentioned here, there's this result of Meeks, Simon, and Yao that said that in this setting, I can put a least area surface between them. So let me explain how you do that a little bit. Okay, so for the surface, say the surface M1, I can take a compact exhaustion of that surface by connected domains. So our first domain maybe has a disk on it, and I just take bigger and bigger domains. So this curve, the curve, so we have this exhaustion, we call D1, D2, whatever, of the first surface. And so the boundary of those domains bound a surface on the boundary. So this, notice that D1 is contained in the boundary of this domain between the two surfaces. And it's homologous to 0. It bounds something. So I could try to solve Plateau's problem in this. So using the same boundary curves, I solve Plateau's problem. So I solve plateau, which means I find a least area surface in this region that has this verb boundary. Okay, so let me just tell you a little bit about how that works. When you have this region here, it turns out it always embeds isometrically into a 3-manifold, okay, which is complete. So this is complete, and what's called homogeneously regular. Okay, it has. You can somehow take the product of this surface somehow with imagine a boundary. I mean, you got to be a little careful here. Yeah. Anyway, compact pieces of it have this property. Anyway, so it's not quite exactly right, but basically, I can take a tubular neighborhood of the boundary on the other side, on the outside here, and that's a product of the surface with a boundary, and somehow I can just change the metric on that. So this manifold actually is just this with a product neighborhood on the boundary. And then I change the metric on that sort of product region and make it be complete. So I have to multiply the flat metric by some function, and I create a new manifold. And if you do this right, it's essentially what's called homogeneously regular. Now, it turns out one can solve Plateau's problem in a homogeneously regular manifold. So if you take a curve and a homogeneously regular manifold that bounds something, it's zero in homology, then you can solve Plateau's problem. You can find, for example, an area minimizing surface that has the same boundary. Okay, yeah. Okay, so we can solve Plateau's problem and get a compact minimal surface. Well, when you do this extension to this manifold, remember you have foliation. You're in a product neighborhood. You can create this metric so that, in fact, the surfaces nearby here have positive mean curvature. So by the mean curvature comparison principle, when you solve Plateau's problem in this manifold, you can, and they're compact, they can't intersect this foliation by the mean curvature comparison principle. So when you solve them here, they actually lie in this subset of that manifold. So this is all kind of, I'm not giving you any details, but it's fairly straightforward. So you solve Plateau's problem in the bigger manifold. You see that the solutions, in fact, lie in the original set. So we substitute this disk by a least area surface homologous to, least area and homologous to the original surface. Okay, and then you just keep on going. And because you solve this in what's called the Z2 homology class, you get you have what's called local area estimates, and you produce this least area surface. Okay. Now, one of the problems when you do this kind of problem is you got to make sure that it's not empty, right? You solve Plateau's problem. Why is it not empty? And that's for homological reasons. If I take a path, remember this is a path-connected space, so I can take a path from this top surface to the bottom surface. And notice this path intersects the original domain in one point. Well, that's a homological property, right? So everything in the same homology class is going to intersect at least one point, this arc, this compact arc. And so I will definitely produce a minimal surface because all those minimal least area surfaces will intersect this arc, so I'll get a minimal surface that intersects this arc, in fact, in an odd number of points. So I get a non-trivial surface that we're going to talk about a little bit. It's going to be least area in that region. In particular, it's what's called stable. So we're going to talk about stable in just a few minutes. What does it mean to be stable? But stable, and we're also going to talk about a nice theorem. Stable implies a plane. So the least area surface between that, which by properties about stable minimal surfaces means it must be a flat plane. And then we're finished. Now you apply the half-space theorem. So in order, the stable minimal surface between them, in fact, is a half plane. It's a plane, and then these surfaces are contained in a half space. And it's very easy to understand what's going on. Okay. So, okay. Okay, so yeah, this is just explaining what I just said. So you solve plateaus problems doing this particular, based on an exhaustion, and then you get your stable minimal surface as a limit of these area minimizing surfaces. Okay, all right. Okay, so one thing that's interesting, you can view the this last theorem as a maximum principle at infinity. You should keep in mind also, this is not true in higher dimensions. Okay. In higher dimensions, you have, in R4, we have catenoids, hypersurfaces which are minimal catenoids in R4, which are they lie in a slab. So they lie in a half space. And you put one here, they don't intersect. Doesn't mean they're flat planes. So this is really a result about something that only happens really in 3 dimensions. It's related to the fact that Brownian motion, somehow Brownian motion is very special in dimension 2. It's a conformal property, where it's not a conformal property in higher dimensions. Okay, so let's see. All right, so if you had these 2 minimal surfaces, M1 and M2, okay, you could say, try to find the distance between them, right? They have some kind of distance between them. And you could kind of imagine just taking this surface. You can think of, given 2 points, I can look at the distance between him. And I can take the minimum of all these sort of vectors between various points. I can take one of smallest length. And it turns out if I translate this one by that limiting vector, I see that the distance between this surface and this surface is 0. I can translate these surfaces if they were disjoint so that the distance was 0. So somehow we'd like to say that if 2 objects have distance 0, that you can't do that somehow with proper surfaces. So we have a version of this theorem that kind of says that. So you have 2 disjoint, connected, properly immersed minimal surfaces in R3, or actually any flat 3 manifold. And suppose at least one, suppose the boundary of one of them is not empty, for example, boundary of M1, then I can talk about the distance between the surfaces, right? The infimum of pairs, a point here and a point here. And I can also look at the distance, say this one has boundary. I can look at, here's the boundary of M1, which is not empty. I can talk about the distance from the boundary of this surface to the boundary, to this surface, right? Whether it's a boundary or not, okay? So it turns out that the distance is always achieved by some point on the boundary of the surface to some other point in the other surface. Maybe on the boundary, maybe in the interior. Somehow, distance is always realized. You can't somehow realize the distance at infinity. The minimum distance happens somehow on the boundary. Okay, it's kind of like a bounded harmonic function has, on a compact surface, has its maximum minimum values on the boundary. It's kind of related to that. Okay, so that's a nice generalization of the last theorem. Okay, where you're allowed to have boundary. Okay. Okay. So notice how would we do in the for example, if this surface and this surface are disjoint, right? Then what does it say about these 2 minimal surfaces? It says they can't have distance 0. They can't have distance 0. I can't do this translation like I said last time. Right? If I had 2 disjoint surfaces, no boundary, I could try to translate them so the distance was 0. Okay, you can do that, but if you do that, then in fact they are just flat. If you achieve the distance by interior points rather than the boundary point, then the surfaces must be contained in planes, parallel planes. Okay, so here's one of the real important applications of this result, and we like this kind of, we like to generalize this kind of theorem in other settings, okay? Because it gives us what are called area estimates. So let's just look at this for a second. Suppose you have a properly embedded minimal surface. Okay, so I'm going to assume bounded second fundamental form. So if the Gaussian curvature is at most 1, and you're in a flat 3 manifold. So for us, this flat 3 manifold is just R3. Just think of, we're in R3. We have a minimal surface in R3. And we look at and what we know something about the Gaussian curvature. It's no bigger than 1. Okay, so now a nice property of that. So if you look at a point on the surface, okay, and here we are at a point, okay, then you have what's called sort of focal geometry of the surface. You can look at all the points of some fixed distance from the surface. So you can take what's called kind of a parallel surface on one side. So let's assume the surface is orientable, and I can just kind of look at the parallel surface on one side, okay? Okay, in fact, I can let epsilon vary. So if I take a little piece of surface, I get this sort of focal surface, right? And the question is, if I take the normal bundle on M, and I go out to distance 1, so I look at all the normal vectors, these parallel surfaces are just gotten by exponentiating the unit normal vector for a certain amount of time epsilon. So if I do that with normal vectors up to length 1, okay, then I get a tube around the surface. I get a tube of somehow radius 1 around the surface. And you can see by focal geometry in R3 and the definition of Gaussian curvature that this mapping into R3 is a submersion. On the open here, there's no focusing. The focusing's good, sort of nice. There's no focal geometry. Like, think of it like a circle in the plane of geodesic curvature 1. It has nice focal parallel surfaces until I get to actually distance 1. Then that mapping's degenerate. So in general curve in the plane, if it's got bounded geodesic curvature, it has a regular neighborhood up to sort of an immersed regular neighborhood up to a certain dimension. The local geometry is nice. So this is a submersion under the condition that Gaussian curvature is less than or equal to 1, an absolute value. What? What? Right, both principal curvatures, right, they're equal and opposite they're opposite in sign and equal in size. So they're, at least you kind of take a vertical plane, you get a curve, and you look at kind of that focal curve. Everything is good locally, but things might not be good globally, right? And you could think of a curve in the plane, it might come back close to itself, right? Even though it's got a nice local picture, right, on one side, those sides cross each other. So it turns out that last theorem, by being clever, you can actually prove that this mapping is actually injective. So the regular neighborhood, regular normal bundle, sort of creates a tube. This is actually going to be 1-to-1. If the original surface had bounded second fundamental form, at most 1, then the submersion is in fact injective. So again, somehow these level set surfaces create some kind of barriers and things like that, and allow you to apply the last theorem by being clever. Okay, but let's suppose it's true. So let's believe that this is a corollary of the last theorem. I mean, it's an argument to show it's a corollary, but okay, so the exponential map is a smooth embedding. We just embed it like straight line segments. So what I mean by exponential map, I'm going to have a vector of some length. I'm just going to get line segments. So I'm looking at all the line segments, orthogonal to the surface of length 1. I'm just looking at those. They don't cross each other. That's what we're claiming. They don't cross each other. They're a nice, normal, regular neighborhood. Okay, so what does that give us? Well, a little thought shows, So in this mapping, I'll do it in the plane. Suppose this is a circle of radius 1, so the curvature is 1. Certainly, if we go all the way to here, this exponential map is bad. But if, for example, I only go halfway, I look at kind of n1/2, okay, and I look at this exponential map here, that into space, that's a quasi-isometry. You have this sort of, it's nice. It's nice in the sense that the area of this ring, which is like the regular neighborhood on one side, because we want to do it on both sides, this regular neighborhood, its area is comparable to the length of the curve. Up by a factor. There's some deformation here, but up to a constant, which you can estimate. You can estimate that constant. It's a universal constant. There's a comparison between the area of the surface and the volume of its regular neighborhood. Okay? In particular, since the regular neighborhood embeds in space, and space has a volume growth, its volume growth is like 4/3 pi r cubed, right? So it has a cubical volume growth. So the area of the ambient area growth of the surface in space is at most some constant times r cubed. In particular, the intrinsic area, which is growing even slower than the ambient area in balls of radius, intrinsic balls, it's also growing only cubically, at most cubically. Maybe it's growing quadratically, but it's not growing very quickly. In particular, in space, the surface, you have what's called local area estimates. The area can't be too big in any ball of radius 1. You have fixed estimates in balls of radius 1 for the surface. If you have bounded second fundamental form, it looks like little graphs. So you get this very nice sort of picture about the surface. Okay. So let me, again, give a kind of a nice compactness result for these surfaces, which maybe next time we'll use to do something, other things that are interesting. So let's just do that for a second. So I'm going to look at a certain space. So I'm going to look, I'll just call it something, call it M. Okay, so this is the space of all properly embedded minimal surfaces in R3. So we're in R3. They pass through the origin. They're not flat. Not interested in flat. And they all pass through the origin. So if I take an M in here, I want the origin to be on that surface. Okay? And I also want a condition about the norm of the Gaussian curvature. Let's assume the Gaussian curvature is always less than or equal to 1 here, and the Gaussian curvature at the origin is equal to 1. So it's -1 Gaussian curvature at the origin. And the Gaussian curvature is less than or equal to 1. This is an example. There are lots of theorems like this. This is just one version of it. Then I claim that is sequentially compact. Okay? Well, and it's also a metric space. So we got to think, what is the distance function between two of these surfaces? So if it's sequentially compact, every sequence has a convergent subsequence. Somehow a compact metric space. So how do we see this? Okay, we said the norm of the second fundamental form is less than or equal to some particular number. The Gaussian curvature is related to the norm of the second fundamental form. We could have said the norm of the second fundamental form is at most 1. But anyway, at the origin, what does one of these surfaces look like? Well, they pass through the origin, right? They have a regular neighborhood. That's what this said. So in particular, there's a small delta that doesn't depend upon the surface. There's a delta bigger than 0 that doesn't depend upon the surface, so that each surface that passes through the ball only intersects in one component, which is the component going through the origin, because it has a regular neighborhood. And it's a graph over its tangent space of gradient at most 1. So graph, small gradient. Okay, in particular, if we make it small enough, its gradient's less than or equal to 1. Okay, so every surface has this property. So how do we see that these surfaces are sequentially compact? If we take a sequence, why does a subsequence converge in R3? And the convergence in R3 is convergence on compact balls in R3 centered at the origin. So if I restrict myself to a big ball under a subsequence, I'll get a limit. And by analyticity, I keep getting the same limit. If I take the limit in the ball of radius delta, okay, then I'll get a surface, okay? And if I always get convergence on compact sets, then I will continue to be the same surface. And I can't get a disconnected surface because of the strong half-space theorem. Okay, so let's think of the local property. Take in this ball of radius delta, suppose you had a sequence of the surfaces. Oh, I didn't tell you the distance function. So what's the distance function between two of these surfaces? Okay, so I have associated to the surface is this little, is M intersect, I'll just call this B, ball radius delta. I have this little disk, okay? And this distance is nothing more than the Hausdorff distance between those two disks. Okay, so that gives a distance function between that little disk and this little disk, and we define that to be the distance between these two surfaces. And it's easy to check that because this is a distance function. It's a metric space. It satisfies the property. This is also a distance function. The distance between two surfaces is 0, then the surfaces are the same, right? Right? These two domains would have to be identical. But they're identical on a disk, they're identical. They're analytic surfaces. So that's the distance function. So take, and these are all compact sets, so that makes you look at all these disks you get, that's somehow a set of compact sets, that's a compact metric space. You're going to converge. Because if you take a sequence of these minimal graphs, a subsequence converges to a minimal graph. Again, with the same small gradient. So at least on this ball, we get convergence. Well, that surface is part of a complete surface. And if you think about it, all these surfaces have bounded second fundamental form, which is uniform. So we can consider them to be a sequence of laminations in R3, right? With sort of uniform estimates on how they look like graphs. But we already showed that a sequence of laminations where you have an estimate on the norm of the second fundamental form converges. That's just a property. So we get a minimal lamination as a limit. But that minimal lamination can only have, okay, yeah, it's a little bit more thing. Just a little thought shows that all those minimal laminations are properly embedded surfaces. There's no limit leaves. Limit leaves are stable. There are no planes, right? These surfaces can't be in a half space. So considering these surfaces as being laminations, we have our standard compactness theorem for laminations. Then we converge to a new lamination, which actually only has one leaf in it. They're all going to be anyway, which is corresponding to the surface, which goes through this point. We again continue having the same estimates for the norm of the second fundamental form on the limit. So we still continue getting the Gaussian curvature is going to be 1 at the origin and less than or equal to 1 everywhere else. Okay, so that's sort of a nice thing. So it turns out that it's a very useful idea, this sort of metric space. Maybe we'll do some things on the last day, some nice kind of playing around with this sort of idea. So this theorem is very useful. It gives us compactness properties for certain sequences of minimal surfaces. Okay, so now we're going to go in a slightly different part of the subject. We're talking about least area surfaces, say with a given compact boundary. In particular, least area surfaces are what I call stable surfaces. So if you have an area minimizing surface, okay, so here's how the boundary, it's area minimizing, then if you move it a little bit, fixing the boundary, that surface is always going to have at least this big an area. So area minimizing surfaces are stable, in particular. The nearby surfaces under deformations fixing the boundary are at least this big. But globally might not be. Remember, the first day of class, I showed some examples of curves that bound lots of stable minimal surfaces. But only one of them was the least area one, the area minimizing one. So we can have local minimums. So being stable corresponds to local minimums. And the language is sort of described in this variation. So we think of compact variation, we're really thinking, look at the part of the surface which is where the variation is non-zero. Anyway, so you have the area function. There's a formula for calculating the second derivative of the area. So if you remember from the definition of the minimal surfaces, there's something called the first variation formula. So minimal surface, the first order are critical points of area. So you can't decrease the first order, but the second order, maybe you can decrease the area. So anyway, so there's a formula for calculating the second derivative, and that gives you something called the Jacobi operator. So you have the Laplacian on the surface minus twice the Gaussian curvature. So that's a Schrodinger operator. It's a Laplacian plus a function on the surface. Okay, so it's an example of a Schrodinger operator. Okay, so, right, so if you look at functions in the kernel of that operator, okay, they don't have to have zero boundary values, just a function in the kernel of that operator. Okay, so the Laplacian of the function is minus 2 Gaussian curvature times the function, or plus 2. Okay, so these particular functions that have a nice property with their Laplacian. Right, so we say that M is stable. Let me stable if it's first. If it should be the second variation of area. It's positive with any complexity. Okay, stable means that the second variation of area. That's a mistake here. First variation. Second derivative is positive. So local minimums for area. Right. Stability is equivalent, so it's nice to have this equivalency because I'm going to use it in a second. Being stable is equivalent to having a positive Jacobi function. So we aren't looking at necessarily functions with zero boundary values. So sometimes people, if you allow yourself to be zero on the boundary, then you have what's called weak stability. So I'm really talking about stability, so I'm going to positive Jacobi function. So a function that's positive on it. Okay, that's at least true when you're orientable. Okay, and so I want to just give a simple application, which is this result of De Carmo and Barbosa, which says that if you look at a minimal surface immersed in R3, and you look at its think of a compact surface, and you look at its Gaussian image. So you have the image of the Gauss map. Okay, so I'm not saying that, okay, so here is our surface in space, whatever. We have our minimal surface. We have the Gauss map to the two-sphere, and it has some kind of image on the two-sphere. So we're looking at G of M. If the area of the surface is at most half the area, is less than half the area of the two-sphere, remember the two-sphere has an area of 4 pi, then okay, then the surface is stable.
That is total area.
What?
That is total area.
Total area, just the area of the image set. And the proof is very easy. Okay, so look at the image set. It might not be smooth. It might have some, the region might cross itself. But let's suppose it's at least the boundary curves were analytic. The set, maybe kind of like an analytic set. It's kind of a reasonable set with boundary. Okay. So the area condition for pi is related. Remember, I'm going to talk about it again in a minute, but we relate the Jacobi functions on M with Jacobi functions on the image. So if you take something in the kernel of this operator on the two-sphere for a domain, then you compose with the Gauss map, you get a Jacobi function. Okay? So that's sort of easiest to see when it's a diffeomorphism. In general, it's a diffeomorphism and you have branch points or whatever. Anyway, but there is a positive function on the image domain for this operator. You just compose, okay, you just compose by G, well, you can check that that's a Jacobi function. And it's positive, right? It's positive, so the surface is stable. So that's all that's going on there. So we're using this slightly. I'm thinking strictly stable means a positive Jacobi function. So we've now created our positive Jacobi function. Okay. Yeah, isolated points where you have branch points, removable singularities when you do this. So. Okay, so I'm going to go back. I want to work on a little bit more in this idea of the Gauss map. It goes to the two-sphere, it creates a domain in the two-sphere. That domain has some kind of stability properties with respect to Laplacian plus 2. So we have this result before. I'm going to just recall the result, but I didn't talk about the proof of this item 3 before. So I'm going to talk a little bit more and actually prove something a little stronger than this. So we have our two convex curves in parallel planes. All right. So we're going to give a pretty reasonable, pretty complete proof of that, this item, that why you have only one or two minimal annuli. So we have plane 1, plane 2. We have our convex curve. And I'm interested in minimal annuli that bound these two curves. So, and we're assuming these curves are convex. So gamma 1, gamma 2, convex curves. And this is M is going to be a minimal annulus. And we proved some things before. We proved some parts of this theorem before. We proved, for example, each plane between the two planes intersects in a convex curve. In particular, the surface is embedded. So we have, on every plane in between, we have a convex curve. The way we did that is we ended up parameterizing it by a flat cylinder that has its boundary, think on these two planes. And the third coordinate function is just the height function on the cylinder. And then being convex created something which created a positive harmonic function on the boundary. Then it was positive, and being positive meant that the level set curves were convex. So there was an argument, which we did before. So we did that. The Gauss map was a diffeomorphism. That's essentially by analyzing what does the Gauss map do on the boundary curve. It gives you a curve which goes around on the two-sphere, another curve which goes around on the two-sphere. Those curves cannot intersect. And by the open mapping theorem, they can't intersect because they miss the north and south pole. And the surface, by the Gauss map, parameterizes a domain in the sphere like that. Okay? And then we realized that once we did that, well, I should just go here. We had the proof. We used this theorem of Schwartz that we can identify the Jacobi operator with this operator on the sphere when it's a diffeomorphism. They're just exactly the same operators when you're a diffeomorphism. So we go back and forth. Something in the kernel, for example, of this operator, we go back to the surface. That's just a Jacobi function. A Jacobi function goes to something in the kernel of that operator. So that's what we did last time. We did not show why the gamma 1, gamma 2 were the boundary of 0, 1, or 2 minimal annuli. So I'm actually going to show a little bit more. I'm actually going to show that not only they're 0, 1, or 2 minimal annuli, I really want to focus that when you have 2, which is somehow generic, if you have something, somehow you're generically having 2, why does one have index 1 and why does one have index 2? Index 1 and 0. One is stable, and one is actually strictly stable, and one is index 1. Okay, so that's a sort of the main thing I just want to point out. How do how do we see this? And hopefully, I was just trying to figure out the best way to do this. So let's go through the proof. Okay, so maybe put the proof over here. Okay, so it's a very general argument. So let me just tell you a little bit about the ingredients of the argument. And this is something I gave a course at Fortaleza back in 1977, I think, before most of you probably were born. So I gave a course on it, and part of the course I talked about the space of minimal surfaces, or space of minimal surfaces bounding a given curve. And that was also about the same time that Brian White was working on his thesis with Fred Almgren. And I went to visit him at Princeton about a year after I gave this course. Okay, so this is related to that. So we have our plane P1, we have our plane P2. Let's see, how restrictive did I get here? Right. Right, convex curves. I'm just going to restrict the way it's set up, convex curves. So I'm going to look at pairs of convex curves. So a general, gamma 1, gamma 2, and let's assume strictly convex curves. So if you move a strictly convex curve a little bit, you get a strictly convex curve. Okay. Right. There's a little question about completeness here, but right, maybe I have to go weakly convex. Okay, so if you do this right, with the right regularity on the boundary, the space of these curves is somehow a manifold. We can look at mergings of them. Nearby mergings are also embeddings. So you somehow have the space of these pairs of curves, and you have above them, you have for each pair of curves, so this is really a pair, gamma 1, gamma 2, kind of is an element in this here. I can look at the minimal annuli which bound these things. So this is the space of all minimal annuli bounding these curves. And we have some properties of this map, okay? So when you do things with regularity, this is you have a Banach manifold. We're restricting the curves to lie on the planes. They aren't just curves in space. You could also do curves in space, but I'm just going to focus on doing it on the planes. And you have curvature and area estimates for these surfaces. Okay, so we have area estimates, we have curvature estimates, and that gives us compactness. So if you take for example, fix the curves, or you have a sequence of these curves converging to another pair, and you have a sequence of the minimal examples, you have a subsequence converging. So this mapping here is proper. It turns out to be proper. So if I take a compact set of curves here, the preimage is going to be compact there. Okay? And some other properties of this map is a Fredholm map of index 0. So I'm going to make an assumption. Let me little space over here. So here's my space of curves. So here's C. Okay. Here's our space of examples. And a point here means a pair of these convex curves. And I'm going to assume, so this is gamma 1 comma gamma 2. Down here we have these two curves. You have a point here. And I'm going to assume that this is what's called a regular value for this mapping. So we can prove that there's somehow, by the compactness property, the regular values form an open subset of the open dense subset. So most points are going to be regular points. So above this point here, if you pick a regular point, I get a finite number of surfaces above. I get something compact, and regular means I have no Jacobi functions. Anyway, you can sort of realize that the preimage of is a finite number of points. And in this setting as well, the number of odd index surfaces, so the number of we have no Jacobi fields with zero boundary values. So we have a certain number of negative eigenvalues with multiplicity, and that's called the index. And the number of odd index examples is equal to the number of even index examples. Okay. In our case, everything's index 0 or index 1 by the previous theorem, because we parameterize the domain in the 2-series. So everything's index 1, index 2, and I have the same, in this case, the same number of those points. Okay. And right, so now I'm making an assumption, right, that we have a regular value, and then you have to kind of argue when you aren't at a regular value, what happens. Actually, what happens when you aren't at a regular value, you either have 0 or 1. And when you have that 1, somehow you're not a regular value. You have a Jacobi function with 0 boundary values. So it's called weakly stable. You're sort of the index 1 example comes together with the index 0 example, and it becomes what's called weakly stable. So that's more of the picture. But okay. So let's see. How do we see that we have only these two minimal surfaces? So let me try to put the proof over here. Let's give the idea. I was trying to remember the best way to do this, and I remember it, then I forget it. So hopefully I'll remember how to do this. So, okay, so the idea is the following. So here's the space of curves. Here's our example that we're interested in. Okay, so over here I'll draw the picture. Curve, plane, plane, plane 1, plane 2, curve, curve, annulus. Okay, so I'm going to go way over here. I'm going to find a path of curves. Okay, so I'm going to write a path in here. Maybe I'll put it over here. So here's our example, gamma 1, gamma 2. Think of this point in the space of curves. And over here, I'm going to put a particular pair, C1, C2. So over here, I'm going to pick two concentric circles, okay? And I'm going to assume that I know, at least at the moment, that above two concentric circles, I have exactly one, and they're big circles. Okay, I have a stable catenoid and an unstable catenoid. So stable, catenoid, unstable catenoid. Okay, and now I'm going to take a curve, which down here, that joins this point to this point. So for example, I could take through convex curves, right? You can sort of take a convex sum of these curves like that. Imagine doing a deformation here through convex curves. And suppose this is in general position with respect to the mapping. So we have pi. Here's m. And I put this in general position with respect to pi. Then the preimage, being that this is compact, is going to be a compact one-manifold with boundary. So since the mapping's proper, it's in general position, the preimage of this curve, alpha, is going to be a compact one-manifold with boundary. Now over here, I'm assuming I have something. Okay, so I have some even number of points over here. Okay, and somehow they have to connect to here. So well, it could be I get a picture like this, right? I mean, then I won't get any contradiction. So that's not what I want to show. I want to show that the ones of index 0, so remember these are index 1 or index 2, the ones of index 0 have to go straight across. So in other words, this curve has a lift. If you start with a stable one, the lift just goes straight across. In particular, and not only that, during this deformation, I stay stable. So if I start with something that's index 0, and I look at the preimage of the one manifold that attaches here, it just goes straight across. And all these examples are stable. If that's the case, then okay, that means there's only one stable one. That means there's only one stable one. And a little thought shows, in fact, you get something like that. So, I mean, anyway, that's going to be the idea. So how do I do this? So I need to start with something stable. So suppose this one's stable. So I got to tell you how to try to deform it. Okay, so the simplest way to deform this is I just look at curves that are constant distance from this curve on the outside. So I look at, think of a parameter t, and I look at the related convex curve here, where this is distance t from that one. This is maybe almost like a heuristic argument. You have to be careful and to make everything rigorous. So I just look at the curve, the related convex curve of a fixed distance away from it. Now, when t is very large, what do I get? Almost 2 round circles, right? When I'm very, very far away, I don't really see much. It behaves kind of like a point. I get almost 2 round circles, which gives me almost a catenoid. And suppose when it's almost looking like 2 concentric circles, suppose I knew that I had uniqueness. So anyway, but the idea is we're going to do this deformation. We're going to start doing this deformation. And this surface here is stable. Okay? So if I move the boundary values a little bit, the surface moves and continues being stable. But the boundary values are moving out. Okay? So you have to see that the surface also moves out. So initially the surface moves out. So we get a positive Jacobi function on the outside, and then because it's positive on the outside, it has to continue being positive inside. So I move the boundary, the minimal surface moves, and it also goes out. So what do I know about the image of the Gauss map for the outside one? What can I say? What's the relationship between the image of the Gauss map of the inner surface and the one that's sort of parallel to it, its boundary is parallel to it? What's the relationship? Well, so remember what the Gauss map looks like. It looks like a curve that goes around like this. And the surface parameterizes a domain on the sphere. So I can look at the points on the same meridian. So here's one image of one Gauss map, and I claim the other one is inside here. I claim that the image of the other Gauss map is a sub sort of annulus of this other annulus. So to see that, I look at the corresponding points, okay? So if I just took the parallel surface, if I'm at a given point here, and I just draw the line over to here, notice that those points are in the same meridian. They have the same tangent vector in the plane, parallel tangent lines. So they correspond to points here. And what I'm saying is that the related point here is going into this domain. So the way you see that is the boundary maximum principle. So we've talked about the interior maximum principle. We want to see the kind of like a boundary maximum principle. So I can translate this inside annulus, just translate it along that direction till I touch it first time. Remember, I go out, so I'm disjoint, so as I translate it around, then I get a picture like this. That I can't touch an interior point a first time, so I must see a picture like this. So here's my outside one, here's my translated one, and they touch the boundary like this. They can't touch tangentially. That's kind of like the boundary, what's called the boundary maximum principle, unless they match up completely, which they don't do. So the angle here at this point where they touch on their boundary is different. And notice which way it is. It's more horizontal. The normal vector for the translated surface is like that, and the other one is more horizontal. More horizontal means I head toward the equator. So you can see that all these related points on the meridians are going in. Oh, that's good. That means I'm not only stable, because I've now parameterized a smaller domain on the sphere, but in fact, I'm more stable. The first eigenvalue of the domain is is even more positive. Okay, so I've shrunk. I made it more stable. And so you just keep on doing this. So I'm stable, stable, stable. That means I just keep on going across. So turns out I go all the way across to here. And then you have to make an argument as why when there are almost two round circles, why do I only have 1 point? Or for example, one else has to prove why if they're concentric circles, why you don't have catenoids. But one just sort of mimics this argument a little bit. So all the index 1 goes straight across. But if you had any more of these things, you can't, when you do this sort of put things in general position, you go like this, the index changes by 1. So you go from index 1 to index 1 doesn't join up like this. Okay, so anyway, so one has to make a few more arguments, but that's the idea. It's just a comparison of what happens as you move the, not just that, I mean, you have to be a little more careful, but that's more or less the idea. So where is my mouse? Okay. But that's the idea. You kind of follow what happens to the stable ones when you go out. And I say this isn't really the actual proof that's in the paper, but it's the idea behind the proof. That the stable ones just continue going because they become even more stable. Okay, and then you can imagine moving, not exactly parallel, but moving, kind of like taking a convex sum and making them actually be round concentric circles. In which case I need to know that I have unique since I have catenoids. Anyway, that's the idea. All right. Okay, so curvature estimates. So this is one way to state the curvature estimates. I think it's a little nicer to use the norm of the second fundamental form. And if you do that, then notice that what you have here, instead of the Gaussian curvature, one has the norm of the second fundamental form, and you times the distance is less than or equal to a constant. So that's probably a little bit better estimate. It depends on what you like, Gaussian curvature or norm of the second fundamental form. So let me just do that slightly different one. Right, so let me just explain why, if you know that the only, I'm not going to do this, you can find this lots of places, and there's some elementary proofs to it. So DeCarmo, Peng, and Fisher-Colbray, they proved that, and Pogorelov, they proved that the plane is the only complete, embedded, stable, orientable minimal surface in R3. Suppose you knew that, why do you get curvature estimates for stable minimal surfaces? How do I do that? So orientable minimal surfaces. Okay, so Ross did a much more delicate argument. He proved it, in fact, stable for non-orientable surfaces. What's nice about orientable surfaces is somehow Jacobi functions Jacobi fields are realized by function times the normal field. So if you're orientable, you have a normal field, and then you can think of the Jacobi operators being an operator on functions, right? And functions behave nicely. You take a covering space, for example, you can lift the functions, the operators lift, and you can do everything kind of better when everything is orientable. So I'm going to just focus on the orientable case, right? And I should say these people proved that the plane was the only complete, stable, orientable minimal surface. Antonio Ross proved the similar result for non-orientable. There are no non-orientable stable minimal surfaces. Okay, all right. Okay, so let me just give you the idea of the proof. Right, so you have your surface M, and suppose it's stable. And we don't have to assume it's compact or anything. It's stable, but something has a smooth boundary. It sort of locally looks like a surface with boundary, surface or surface with boundary. So we have some kind of, but think of it even compact. So we have a boundary, gamma is the boundary of the surface, and you do this what's called the standard blow-up argument. So by going to the universal cover of M, I can assume this is simply connected, right? Connected. Just makes it a little easier to So I'm just going to, in my pictures, I'm going to draw, for example, just a disk. Okay? So here's our surface, and if I take a point in it, I can look at the distance function from the point to the boundary of the surface, the intrinsic distance. Okay, so I can look at a minimizing geodesic to the boundary. I'm going to pick what are called points of almost, well, maximal curvature. Okay? All right, points of almost maximal curvature. What does that mean? So it's, okay, if the surface is compact, then I can pick a point P. I can pick a point P with the following property. P is a point where is it? Yeah, I didn't do this too well. Okay, so let me redo this thing. Let's don't assume the surface is compact. Okay, suppose, I'm sorry. I'm also trying to get the following equation. The norm of the second fundamental form of M at P times the distance to the boundary, P to the boundary of M. I want to show that this is less than or equal to some constant. So let's suppose we could find a sequence of surfaces, a proof by contradiction. Suppose I could find a sequence of surfaces, a sequence of points, and this is big, right? That would be the contrapositive. So suppose it fails, then you'd be able to find a sequence of compact minimal surfaces, points in the interior, so that this product was actually large. So for each one of these compact surfaces, I'm going to pick a point. So I'm going to pick point P, N. Oh, I can assume this point is a maximum for this function. So I take the norm of the second fundamental form times the distance to the boundary. And I can do that, varies continuously, and the distance to at the boundary is 0. So I don't achieve the minimum at the boundary. So I can assume that these points are points of what are called maximum curvature. Okay, maximum, where this product is maximum. Product is maximum. Okay? I'm going to translate those surfaces to the origin. Okay? And I'm going to multiply, scale them by the norm of the second fundamental form at Pn. Okay? So this creates a sequence of minimal surfaces. What's bad is, I don't know, these surfaces might not have bounded second fundamental form. And we saw today, when surfaces have bounded second fundamental form, they have nice compactness properties. So I'm going to vary this construction. So here's our original surface. Here's a minimizing, here's Mn. Here's a minimizing geodesic gamma n to the boundary, which has length d. This number is dn. Its length is dn. Okay? And I'm going to pick the intrinsic ball at Pn on Mn of 1/2 dn. I'm going to look at the points of distance dn over 2 to Pn. Okay? All right. So I have this little piece of surface. I drew it like a disk. Maybe it's not a disk. But anyway, it's a compact minimal surface. And I'm going to scale it. I really want to restrict, instead of to the surface, I'm going to restrict to that ball. So B, M, N, P, N, 1/2 dn. Okay, so I'm going to just translate this part. And the reason I'm going to do that, after scaling by this sequence of surfaces, which are called, say, MN hat, these have bounded second fundamental form. Bounded for, okay, so the norm of second fundamental form of these surfaces is bounded, I think, by a half. So remember, the second fundamental form was very big here, but you can check that if you take any other point in this intrinsic ball, it could have larger norm of second fundamental form, but by the way to define it, its norm of second fundamental form can't be more than twice as big as this. Right? It could kind of, maybe for example, it could be exactly twice as big at this point, and it's going to be smaller over here. These points are further away. So a little algebraic calculation shows that the norm of second fundamental form could be a little bit bigger on this surface than here, but only by a factor of 2. So when I scale by this, I make the norm of the second fundamental form less than or equal to 2. I'm sorry. Okay, so this sequence of surfaces, M and hat, have bounded second fundamental form, at most 2 in R3. And they all go through the origin. So now I just want to look at that little, what happens at the origin. So here's the origin in space. I'm going to take these surfaces. They've already been translated, so they pass through the origin. And again, because they have bounded second fundamental form, there's a small number, delta, small, right, positive but small, so that the surface that goes through the origin at this point is a component, and it's a graph of gradient at most 1. Small gradient. You can make it smaller if you want, but so this is a minimal graph passing through the origin. So what I want to show is a subsequence of these M n hats has in it a stable, complete minimal surface. There's a limit. I can take a limit of the right subdomains on the surface and create a complete, stable minimal surface. Okay, so if I look at these surfaces, so Mn intersects this ball of radius delta, center at the origin. I have components. These components are called delta n, which are graphical. These components, being graphical, a subsequence converges. So a subsequence after choosing a subsequence, these delta n's converge to some delta infinity. So I'll get a graph passing through the origin. I claim that that's on a complete, stable, minimal surface. Okay, so you have to, so it certainly lies on a complete minimal surface. You have to see, take a biggest, this is analytic, you had bounded second fundamental form nearby here. You can prove that delta infinity lies on a complete immersed minimal surface in R3. So that's sort of a continuation argument. And then you need to check that this is stable. Well, compact pieces of the surface are converging onto this, and then you have to see that when the surfaces are close, one is stable, the other one is also stable. So with some arguing, this is also stable. But it's not, it's complete, stable, and now you apply the previous result that says it must have been a plane. But these surfaces had norm of the second fundamental form 1 at the origin. So they're not planes, they're not flat. So there are some little arguments here that one needs to do, but somehow you get a surface that's bounded second fundamental form. This is actually a complete minimal surface of bounded second fundamental form in R3. And then we also know in this case, we're actually proper. We have regular neighborhood. Okay. Oh, no, we don't know it's embedded. I'm sorry. Right, the original surface wasn't embedded. Anyway, we have bounded second fundamental form on the surface. Anyway, so that's somehow why the non-existence of stable, complete minimal surfaces in R3 give rise to curvature estimates. It's natural. It's a natural process. And when you go in the manifold setting, you have to be a little more careful. And Harold and Schwam, who else is on, and Eric Tubiano, they somehow showed how to generalize this argument in to do something to get curvature estimates for stable constant mean curvature surfaces in manifolds where you have an estimate on the sectional curvature of the manifold. And again, they do it, but they only do it for orientable. Presumably, you can do it for non-orientable, but they did not do that. Okay, so anyway. So one of the, again, nice consequences of the first theorem, that stable means it's a plane, somehow, and these curvature estimates here, is one sees that if you have a complete immersed minimal surface in R3 with a compact boundary, and it has finite index, then in fact it has finite total curvature. So this is, a plane certainly has finite total curvature. So somehow it gets very, very flat enough so that there's no total curvature on the ends. So you have a finite number of ends. And this is related to if it has finite index, you have a complete minimal surface with compact boundary. Outside of a compact set, it's actually stable. And then stable has finite total curvature. And in a compact domain, subdomain that's left over, it's compact, so again, that's only a finite, the integral of the Gaussian curvature is again finite on that. So it again comes back to being stable. Stable, complete, compact boundary, it means you have finite total curvature. So I'm not going to talk about the proof of that either. Okay, another key technical result is that one has what's called the monotonicity formula. So if you look at a complete, connected, properly immersed, proper is important, minimal surface in R3, and you look at the area of the surface inside of a ball of radius r, okay, then if you take the area divided by r squared, then that's monotonically increasing. Okay? In particular, if you put the surface passing through the origin, then you see the area at the tangent space of the origin is like pi r squared. Then you see that you get this that the area growth is at least like pi r squared in R3, and in fact equal to pi r squared only if it's a flat plane. So just by making sure the surface went through the origin, then this gives you, and you know the infinitesimal property of a minimal surface is its tangent plane. Tangent plane looks like pi r squared, the area growth. Then you get this property, this last property. Okay, which is, anyway. All right, pressing the right buttons. Okay, so that's a key result. Right, it's used a lot in analyzing singularities of minimal surfaces. Right? I should say it's very important that it's proper. Proper is really important. I'll give you an example of something we don't know in higher dimensions, in Rn or R4, for example. This is related to something Harold told me the other day, so I'm just wondering what he's going to have to say anything about this. One of the neat things one can do is, it turns out you can look at foliation, minimal foliations. Okay, so if you have a minimal foliation of a manifold, then the codimension 1, we're interested in codimension 1. Okay, so for example, R3. You have a minimal foliation of R3, then it turns out the only possibility in R3 is F is parallel planes. Because when you have a minimal foliation, it's not hard to prove that compact subdomains are area minimizing Okay, a transversely oriented foliation. You take a compact subdomain on a leaf, any other surface Z homologous to it that has the same boundary always has bigger area. So you do something with the divergence theorem. So not too hard to prove, but they're all stable. In particular, all the leaves are stable. If you're in R3, the only stable minimal surfaces were planes. And so in R3, the only thing that can happen is a foliation by parallel planes. So it's an interesting question, what happens in R4? So can you foliate? So if you take a minimal foliation of R4, and by you could even assume for me that this foliation has bounded second fundamental form. If you have such a minimal foliation of R4, you can actually produce one that has bounded second fundamental form. So locally, it looks really nice. Locally, in ball of radius, small size, everything looks graphical, very, very nice picture locally. But is it always a foliation by hyperplanes? So the surfaces are area minimizing. Well, now, if they were proper, that would be true. There's a theorem. So if the leaves were proper surfaces in R4, then, yeah, they're hyperplanes. But the problem is that maybe none of them are proper in R4. Maybe they're dense in R4. Maybe they're really bad. So it's an interesting question to what extent, even under very strong hypotheses of being area minimizing in R4, when can you prove something like we have in R3? Stable implies planes. Now, it could be true. We just don't know what happens. We don't know that really basic question when you go one higher dimension. Area minimizing surfaces, are they hyperplanes? Maybe, maybe not. Anyway, it becomes a very interesting question. And it's somehow related to, when you're proper, you get sort of nice estimates about area, how the area grows. Okay, so remember we have the Weierstrass representation. We have I'm just putting this up again because it's maybe been a while since people saw that. If you know the meromorphic Gauss map, you have this form DH. You create a holomorphic form. You integrate, you create minimal surfaces. Okay. Well, from that, we have this. I just put this up. It's good to have, especially since they're taking videos of this. It's nice to have somewhere these formulas that you can get from the Weierstrass representation. Because I certainly never remember them, and then I'll go back to my own slides and say, I know there's somewhere where I can write down all these things. So R here refers to the real part of this, okay? So there's a lot of data here. Anyway, there are formulas that are useful sometimes for doing calculations. You really want to know what is the Gaussian curvature. You want to make an estimate for how you write geodesics on a surface joining 2 points when you know something about the norm of the second fundamental form. So you need to know explicit parameterizations. You need to know what are the formulas explicitly. So those are just kind of nice to have. We've talked about this before, the absolute total curvature is the inner of the Gaussian curvature. And let me just tell you a little bit about this. There's a famous result of Huber, is it Huber? Huber, who studied just in the Riemannian setting. So he looks at a Riemannian surface, and he says, suppose that surface has non-positive Gaussian curvature. I mean, he did something a little more general, but let's just think that in the realm of surfaces in R3, we have non-positive curvatures. And if you integrate the absolute value of the Gaussian curvature, suppose on that surface that's a finite number. And suppose the surface is complete. So complete surface, non-positive curvature, and suppose the integral of the Gaussian curvature is finite. What can you say about the conformal structure of that surface? And it turns out Huber proved that the surface is always obtained conformally by a compact Riemann surface with a finite number of points removed. So it's very explicit. So if we're looking at for a minimal surface in R3, with finite total curvature, we know something about the conformal structure. Okay? So that's what Osterman said. Say, well, Huber has this very nice theorem. Let me try to apply it to understand minimal surfaces with finite total curvature. So complete, say, orientable, just to make everything easier, orientable minimal surfaces with finite total curvature. Not orientable, take the two-sheeted covering, then it's orientable. I don't change the integral, just changed by a factor of 2, it's still finite. So if you want to understand non-orientable, let's just take the oriented cover. So this is pretty general, but we're making an assumption that this maybe is finite. Okay? So what can you say about these surfaces? And remember, the integral of the Gaussian curvature is just nothing more than by change of variables, it's nothing more than the area of the Gauss map with multiplicity. Okay, so here's your surface. Okay, here's your surface here, a compact surface, and our actual surface is we move a finite number of points from it, Pn. And that's conformally what our surface is, right? So we have maybe some handle, we have maybe genus 3 surface in this picture. So both our surface has finite total curvature, and we're in R3, and this is the conformal structure. So we have a finite number of points we removed from it. Well, notice outside of little disks around these points, those are just punctured disks. So we can parameterize those little disks around some pk by a punctured disk. Everything else here is compact. So the integral of the Gaussian curvature over this is finite, somehow covering up the sphere. And we want to understand what happens as we go near these points here. We know we have finite total curvature. So if we restrict the Gauss map to a little disk here, we can assume that the area with multiplicity of G is, I don't know, as small as we want, less than 1, right? Counted with multiplicity, because we have finite total curvature. To make these very, very small little punctured disks. Okay. All right. So in particular, when we restrict the Gauss map to the punctured disk, we must miss a lot of the sphere, right? If the area is only 1, the area of the sphere is 4 pi, there are whole open sets in the sphere that we're going to miss, right? So when we count with multiplicity, it's 1. So the area is certainly less than 1 as well, right? So we're going to miss. But now we have a holomorphic function. We can think of missing the North Pole with stereographic projection. So now we have a holomorphic function on the punctured disk, right? And now you apply Picard's theorem. You can't miss a whole open set on a punctured disk, right? Unless you're constant, or unless you converge to a value. So you have to be able to extend the Gauss map across. In other words, it's a removable singularity for that holomorphic function. So that means you have a limiting tangent space or limiting normal vector as you travel along the ends. Well, a little thought about that means that the surface looks graphical over its somehow limiting tangent plane at infinity. It might spin around a few times, but it looks graphical. Anyway, you got a nice picture for what the minimal surfaces look like. And in particular, you have the data, this meromorphic data. The Gauss map, in particular, we just saw extends. And a similar kind of thinking shows that this differential also extends meromorphically across the punctures, which means everything is given by meromorphic data on a compact Riemann surface. So all the data extends to the Riemann surface. And so that's really, really helpful. So we're going to, for example, let me see if I can draw pictures. For example, we're going to come to those in a second. Right. So, OK. So from that extension, that sort of nice property of we can understand asymptotics of finite total curvature minimal surfaces at a puncture. And in particular, a very nice representation when it's embedded. So when the end is embedded, you can think of it as a graph over a big annulus in the plane. So it's outside of a disk. So the surface looks like a graph, minimal graph, over something, so we have some kind of a graph over here, and we can write down the asymptotics of what that graph is. So this was done by Rick Shane. You can just get a real good estimate. You get some kind of term which is called the logarithmic growth at the end, which is the A value there. This is somehow just a translation, right? Like translating up and down, and then some decay on the other coordinates, okay? And that's useful for doing something he was interested in, which I don't know if I said it, I probably didn't say it. But he used this representation, this estimates, to prove that if the minimal surface is embedded, has two ends, and finite total curvature, then it must be a catenoid. So he kind of used sort of strongly this very specific representation to see the ends look like catenoids, and not only that, they're placed sort of nicely. They have somehow the same axis. Okay, and he used a reflection argument to get the rest of the proof. Okay, so A is called the logarithmic growth. Anything else important here? Right, and you also get from this that these ends must be asymptotic to actual catenoids or planes. So every end of finite total curvature, when it's embedded, is actually asymptotic and to a plane or catenoid. Okay, so we have the actual catenoid with its data. Okay, we have these examples written down by Costa. Okay, so what do we know? This particular example is a genus 1 minimal surface of finite total curvature. What are Riemann surfaces of genus 1? They are elliptic curves, and they can all be realized by the following way. Every conformal torus is conformally equivalent to the complex plane, and you divide out by two independent translations. So you make a lattice of translations, you divide out by two independent translations, you have the fundamental domain for it, so you make this a flat torus by gluing opposite sides together, like that. So you make this flat torus. On every flat torus, one has the Weierstrass P function. That's a meromorphic function. And you can take its derivative. Derivative actually makes sense for the Weierstrass P function. And that turns out to be going to be his Gauss map for creating the surface. So P prime, the derivative of the Weierstrass P function somehow becomes the Gauss map, multiplying by a lambda. Of course, you've got to pick the right V1s and V2s. So that's better than a square. So E1, E2, and you can say you pick the right number here, take the derivative of the Weierstrass P function, and I think if I remember, maybe is it dz, maybe, so dh is this, or maybe it's this divided by the Weierstrass P function. Anyway, you can write down possible data for a minimal surface. You can write down a possible meromorphic Gauss map, and you can write down a related form. And what he did in his thesis is he showed that he could write down this data so that he got a minimal surface in R3 that's well-defined. So there's a Weierstrass representation. Of course, he has to remove some points from the source. So he removed, if I'm trying to remember, these, I guess, I'm trying to remember, yeah. He removes 3 points from the torus. So here's my square. He moves the identity element, this point, and this point, these half lattice points. That's then that's the torus. The center point is somehow, there's some symmetry on this surface, right? There's some rotational symmetry, there's some reflectional symmetry. So those symmetries, like reflectional symmetries, end up going through this particular point, and there are also some straight lines on the surface. And so there's a special point where the vertical axis of symmetry intersects the surface. So that's going to be this very special point on his square torus, But you write all this down, it's not easy to see if the surface is embedded. So I remember him coming to me and said, well, I got this surface. I know outside of a compact ball, outside of a big ball, the surface is embedded. So how do I know that? Well, the top end is asymptotic to a catenoid going up. The middle end, the part in the middle, is asymptotic to a horizontal plane. And the bottom end is asymptotic to a catenoid going up. So outside of a big ball, it's embedded. But I don't know what it looks like. It's very hard to know what it looks like. So it turns out David Hoffman and I, we made pictures of this surface, and then we said, aha, it is embedded. Wow, he's got a really nice example. This is several years later. So we make pictures of it. Computer graphics had taken off by then. Well, not taken off. We developed our own kind of computer graphics. Anyway, at some point, we see that the surface is really embedded. And we also tried to understand it a little bit differently. And we tried to see how to make these surfaces. So how do you make a Riemann surface? So one way to make a Riemann surface is take a polynomial in a complex variable z, a finite order polynomial. I can view it as being on an extended complex plane. Maybe it's got a pole at infinity. But I can take that plane, and I can look at all the zeros of this. Okay, it's a polynomial degree n. And I could, for example, maybe make these zeros to be, anyway, I could take a polynomial, and I can take a root of this polynomial. I can take the root of this polynomial. That's well defined on a two-sheeted covering of the surface, of the sphere, the punctured sphere. Or I can take an nth root of such a polynomial. That creates, somehow I can think of this as living inside of C cross C with infinity extended, right? You have the roots, and you have the Z, the complex number, and its various roots of the polynomial. Anyway, you can see these surfaces as Riemann surfaces, and you have various projections. You somehow have the Z projection, and you have the roots. Anyway, you get some meromorphic data. From that meromorphic data, you can reconstruct potential minimal surfaces. So we wrote down the right polynomials. We created surfaces with lots of symmetry. We used the symmetry to prove the surfaces were embedded. And closest examples are in the sequence of surfaces that we made. So we just kind of made some more pictures, right? Made some more examples. Okay. And it turns out all these examples that we made, they, go back one time, they all had the property that they had a middle end, which was asymptotic to a plane, a top and a bottom end asymptotic to catenoid ends. And I remember doing this, I think it was at Rice University, stayed up late at night, and I started making pictures of this surface. So I said, well, maybe we can move the middle end. Maybe there's a parameter. I can move the data by a parameter. I can change the Gauss map by multiplying by a real number. It's just another meromorphic function. And I can change the form by dividing by a number. And if I do that, and I could see maybe I can solve the period problem, and I can deform Costas' example. And when I do that, the middle end that used to be a plane deforms to not a plane, but to a surface that's got a very small logarithmic growth. So it's very close to a plane. So you can deform these examples. And with some more work, Karsha, so we showed how we could deform these. And then Karsha and Hoffman actually proved that this deformation always creates embedded surfaces. So ends don't cross, things like that. And that they exist for every value of the parameter. So they kind of went through and did some more calculations. Okay, then we come to this kind of question. So that's one way how you can make finite total curvature surfaces, right? You create, maybe by polynomials or by other methods, you can create finite total curvature surfaces. Then we have these infinite total curvature examples of finite topology. So the Gauss map here doesn't have finite area. It covers up the sphere an infinite amount of times. So we have, we talked about this a little bit before. You can add a handle to a helicoid. You can add two handles, right? This is somehow the same picture. So there's one handle here. Here's a handle added here and another handle added here. And if you just keep on doing this and you make these pictures and you start seeing something which is these surfaces, they have a vertical axis. They all have a vertical line on them. They have another line which goes this way, kind of like here, like over, I guess you can see it over here. There's another line on here of symmetry that's horizontal. And if you rotate around two lines going through the origin, you rotate by 180 degrees, that gives you another rotational symmetry. So that is a rotational symmetry of a line that's perpendicular to the surface, right here. Okay, so anyway, I don't know if you can see that, but there's like a line this way. It goes horizontally that way. So we have a line on the surface this way, a vertical line, and then the rotation around the two gives you a symmetry. And along that line, it turns out you can keep adding handles. You can add handles. And what they look at as they go out sideways, they start looking like catenoids. It's like you add a little catenoid to the helicoid. Anyway, that's what you make when you make the pictures. And as I said before in an early talk, that Hoffman and Trazé and Brian White, they actually proved existence of somehow surfaces. Who knows if their surface is the one that's there, the genus 1, but they proved there exist surfaces. So one of the conjectures is, are the ones they produce unique? Are they the ones we always make? Are they the same surfaces? Is there really only one, which is the one we make when we solve period problems, and we make a picture, there's the surface. Is that the only one that happens? So it's a very interesting question. Okay. One of the reasons I'm showing this example, very simple Gauss map, right? We have G of Z equals Z, very simple form, Z dZ, right? Very simple, everything's very simple here, right? So simple Gauss map, simple meromorphic data. Its complex plane is the Riemann surface. You plug that into the Weierstrass representation. You integrate from the origin, which is this point right here. Fix the origin, the complex plane. That's going to there. And a little thought shows that if you go back and look at remember the Weierstrass data produces information about the second fundamental form, the first fundamental form. It's not hard to see rotation and the complex plane. To rotate around the origin of the complex plane, that's an isometry of the complex plane, but it's also a isometry in the induced metric on the surface. So the NMP surface has on it a one-parameter family of intrinsic isometries. Okay? Some of them extend. Most of them don't. Some of them extend to ambient isometries. Okay? Anyway, it has some nice properties. And I'm going to talk about a little bit more about extending symmetries. Okay, you also see it's algebraic, right? It's one of the most minimal surfaces, certainly embedded ones, are not algebraic if they are in a plane. So being algebraic is pretty tricky, but NMP is algebraic. There you go. It's got polynomial. It's a zero set of some polynomial. Okay, we have helicoid, very simple. We talked about it quite a bit. So now we get to the isometry conjecture. So remember, NMP has on it a one-parameter group of intrinsic isometries. In its intrinsic metric, it has one, but it's not a surface revolution. Right? It's a circle family of asymmetries, but they don't extend usually. 180 degrees extends, but most of these rotational symmetries don't extend. Okay, so this is oh boy, I thought I was going to fix that. Okay, so M element of graphic C in red, that's supposed to be complete minimal surface. And I think I did this on a different time I was doing the lecture notes. I wrote it all out, but then when I stuck everything in here, I stuck in something which wasn't right. So anyway, this just means a complete embedded minimal surface in R3. Then the claim is every intrinsic isometry, so it's an injective complete immersion. Then the claim is every intrinsic isometry of the surface extends to an ambient isometry in R3. So this is one of these great problems. I think in my lifetime somebody will figure it out, but I certainly work on it every year a little bit. Okay, so furthermore, if you're not a helicoid, so a helicoid is simply connected. If you remember, when you're simply connected, you can change the Gauss map, or you can change the one form by multiplying by e to the theta. Okay, you can somehow rotate. Anyway, you can deform. You can get what's called the associate surfaces. So if you have a simply connected minimal surface, you can keep the Gauss map, and you have a new. You change the form by just multiplying by e to the theta dh of the old form. So you keep the Gauss map doesn't change, but you rotate the sort of what's called the height differential. Then locally, if that's locally that will give you a minimal surface. If you're simply connected, it will give you a new minimal surface, and that minimal surface it's always well defined if it's simply connected. So this gives you a new surface called the associate surface, always defined on the universal cover, for example. Okay, and so where are we here? Right, I'm sorry, go back. So the claim is if you're not the helicoid is simply connected, then you are minimally rigid, which means if you take any other isometric immersion, right, so you haven't changed the metric, into R3, then that immersion is gotten by an ambient composition with an ambient isometry. In other words, you can cover. It's well defined. I can just on the universal cover, I can take the associate surfaces, but they're not properly embedded. They're not. We just got big issues. So okay, so that's one thing. Then we know this is true in lots of cases. So okay, so let me just say some things about some other things we've talked about before that would allow us to try to do this. One thing we'd like to say is we don't have to assume some aspect of this conjecture. We don't need to assume that we are complete. We could say properly embedded. Suppose we could prove it for properly embedded. Does that imply it's true for embedded? There are questions like that. Proper is better. How about bounded second fundamental form? How about if we assume bounded second fundamental form? Would that make it easier? Well, notice it is easier if we make certain hypotheses, right? Like being doubly periodic. So some of the things I'm going to talk about next time are related to take a general minimal surface. How do I make from it limits which are somehow better minimal surfaces? So for example, like the surfaces that we had today, we were looking at earlier today. So I don't know if you remember that we had this, I don't know what time it is. Oh, it's past time. Okay, so I'll continue talking next time. I completely forgot. So I'll be talking about how do you get new limits from a minimal surface that may be bad in some ways, and the old problem transfers to the same problem on a much better surface. And maybe we can solve the problem for that better surface, thereby solving it for the original surface. So, for example, the symmetry problem, we make it more special, more hypotheses. Solve it with more hypotheses, we solve it in general. We solve it in the general case. Okay, so that's it for today. One more lecture, and that's next time. I don't know if Harold has anything to add about anything. Okay, I'm going to be leaving on Thursday, so I'm going to be giving the lecture, and evidently Lucius said he would be willing to take me to the airport. So I could be around a little bit later on Thursday, but I'll certainly be here for a little while today. So if you want to talk to me about anything, today would be a good day. That's it for today.